In this video, we look at probabilities using some counting techniques, so probabilities that involve some of the permutations and combinations. So we'll just look at a few examples. The first one is, what is the probability that a group of 3 students chosen from 7 will consist of the 3 brothers, with the oldest as president, the second oldest as vice president, and the youngest as secretary? I'm going to start with a little bit of a picture here. Let's start with our picture. We've got our president, our vice president, and our secretary. If the oldest person is going to be the president, there's only one way for that to happen. There's only one way for the second oldest to be vice president, and only one way for the third oldest to be secretary. So the number of desired outcomes is only 1. 1 times 1 times 1 is 1. So that's our number of successful outcomes or desired outcomes. So that's NA is equal to 1. Now we just have to find NS. So NS is the total number of outcomes when we look at 3 different positions. So again, let's have a look here and see what that looks like. 1, 2, and 3. There are 7 people in total. So we have 7 options here, 6 for the vice president and 5 for the secretary. That's also the same as a permutation of 7 objects where we're taking 3 of them. So that's NS. So then the probability here of this happening, call it A for now. So the probability of A happening is just NA over NS. And NA we've already determined is 1. There's only one way this outcome can happen, and the total number of possible outcomes was this permutation. We didn't write it down here, but if we go to our calculators, we'll get 210 there. So the probability of this happening is 1 out of 210. Again, we can express that as a decimal, as a percent, or we could just leave it as a fraction. So we can conclude, therefore, the probability of having the 3 brothers with the oldest as president, the second oldest as vice president, and the third as secretary is 1 out of 210. All right, let's change the question slightly. And let's look at what is the probability that the brothers will be chosen and their order doesn't matter. So again, we have these 3 spots, the president, the vice president, and the secretary. So we're saying we want to choose these 3 brothers. We don't really care what order they're here. Well, that means that there are 3 choices for the president, 2 for the vice, and 1 for the secretary. Or 3 factorial ways to make a choice. Again, those are desired outcomes, so that's NA. 3 factorial is just 6. And then we can calculate NS. See if I can squeeze that in over here. So NS is the total number of ways that a committee could be formed. Well, there are still 7 people. We still need 3 of them. The order is still important. So we need to make sure that we're looking at a permutation of 3 objects taken from 7, or 3 people in this case. So the total number of outcomes is the same as it was before. So the probability of this event happening is going to be 6 out of 210, and again we should reduce that fraction because we can. 6 divided by 2 is 3, 210 divided by 2 is 105. So therefore the probability that we can get the 3 brothers in any order is just equal to 3 over 105. Okay, let's move on now to a second example, a little more complicated this time. Question's asking, what is the probability that 2 or more students in a class of 24 are going to have the same birthday? So we want to know, what is the probability that 2 or more have the same birthday? The result here actually might surprise you. Well, really, the results that 2 or more people having the same birthday is really that the probability that there are 2 people with the same birthday, or the probability that there are 3 people with the same birthday, and so on. So we would have to actually do this all the way up to the total of 24 people having the same birthday. That's a lot of calculations, So instead, we're going to find another way to do this. We're going to go and use the indirect method here, and we're going to look at what is the probability that no two people have the same birthday. So, and the reason for that is that the probability that two or more have the same birthday is just equal to 1 minus the probability that no two people have the same birthday. Now this probability that no two have the same birthday is not super easy to calculate, but we'll go ahead and we'll try to have a look here. So let's just say that we have two people and we want to know the probability of them having a different birthday. So here's person number 1, here's person number 2. Person number 1 has a birthday. What's the probability that person number 2 has a different birthday? Well, we'll forget about leap years for now, we'll just assume it's a non-leap year. There are 365 days in the year. If person number 1 already has a birthday and we want person number 2 to have a different birthday, then they have 364 choices for days. And that's going to be out of the total of 365. Well, let's add in a third person now. The third person, if we're going to have 3 people with different birthdays, the third person only has 363 possible days to choose from out of 365. So I think you can probably see a pattern emerging here. The fourth person has 362 days out of 365. And we would continue this until we got to a total of 24 people. That's a very long and tedious process. So instead, what we're going to do is we're going to find a pattern here. So the pattern is notable. Let's start in the denominator. We can see that there's a denominator of 365 times 365 times 365. Notice that for 4 people, our denominator was 365 to the 3. 365 multiplied by itself 3 times. So let's move on to the numerator. The numerator started at 364 and went down to 362. So this is for 4 people. So remember, there are 365 days in the year minus 362. So I'm just looking here to see kind of what difference we had. This is a difference of 3. So can we use this information then to figure out what we need? Actually, I'm thinking maybe instead of that, let's look here. We started at 364, and this is a permutation of some number of items. But notice here, when we went with 4 people, we only needed a permutation of 3 items. So this is actually P364, 3. Couple things to note here. The 3 on the exponent and the 3 in the permutation were the same. And in our example, we had 4 people, so these numbers were 1 less than each other. On the question we're doing, we're looking at 24 people in total. So let's see if we can kind of generalize this. I'm going to keep that 1. So the probability that no 2 people have a birthday then is going to be a permutation where we start at 364. And because we're looking at a class of 24, we need to look at 1 less than that number. So we're going to go to 23 here, divided by 365 cubed. So again, the 365 to the 23. The exponent on the 365 in our example was 1 less than the number of people, and the number of items that we were taking for our permutation was also 1 less than the number of people. So there were 4 people, but we only did a permutation where we were taking 3 items because that first person gets that first dibs at a birthday. So now we can evaluate this, plug it into the calculator, evaluate the numerator and the denominator. I don't have it broken down, but I know that the entire probability here works out to 0.46. And again, we want the probability, so that's that no 2 people have the same birthday. We want to look at, the question asks us for what's the probability that at least 2 people, so this could be 2, 3, 4, 5, all the way up to 24. So 1 minus that probability will give us 0.54. So that means that in a class of 24 students, there's a 54% chance that two or more people will share the same birthday. Therefore, the probability is 0.4554, pardon me. Or 54%. That was a little tricky, going about using the indirect method, finding a pattern in the denominator and the numerator of our no two people having a birthday, finding these patterns. And it's helpful, I think, in this case to look at a small example just like we did over here. So if we look at a small example, we can sort of match some of these numbers and extend that idea further.